Today, I will talk about knowledge graphs and how modern large language models, or LLMs, enable creating and querying knowledge graphs and graph databases in general. I would also touch upon graph RAG, which is a novel way of implementing retrieval augmented generation with knowledge graphs. So let's start. From data to information to knowledge, the quest for getting the right answer to questions has made most information retrieval problems as search problems. It's a search on structured, unstructured, and semi structured data. While the quest for knowledge among information systems continues, a knowledge graph provides a real glimmer of hope, preserving intricate relationships of knowledge systems within nodes or entities and relationships, and respond with a clarity which is not possible to expect from traditional RDBMS systems. A knowledge graph armed with an ontology, which is the metadata about entities and relationships, present a reliable and accurate means of getting the right answer from our data. An open source graph database like Neo4j greatly simplifies building a knowledge graph for an organization and can enforce schema or ontology definitions from domain experts, thus creating a robust information retrieval ecosystem. The example here shows a property graph model or a knowledge graph of a supply chain. You could see the nodes or entities like carrier, like shipment, vendor, inventory, product, customer, etc., which are interconnected with relationship, like inventory pulls shipment, carrier delivers shipment, inventory contains products. So in these cases, contains, pulls, and delivers. These are all relationships. So the nodes are entities and the relationships together creates this organized representation called a knowledge graph, which is typically stored in a graph database. But in reality, not all structured and unstructured data is a knowledge graph. On top of it, extracting ontology information using named entity recognition, or NER, and other natural language processing processes take considerable effort to extract, consolidate, validate, and assess the metadata. So all of this makes creating a knowledge graph constrained by the ontology definitions a difficult proposition so far. Now, with the advent of modern large language models, LLMs, thankfully creating knowledge graphs and querying graph databases to extract information from the knowledge graph has become a bit easier. LLMs facilitate knowledge extraction in three ways. Number one, extracting knowledge graph from unstructured data and creating a property graph model. Number two, querying existing graph databases using natural language, where the LLM converts the natural language question into Cypher, which is the SQL for a graph database. And number three, implement a graph RAG for grounded knowledge graph based retrieval augmented generation. We will explore all these three in the next slides. So in summary, modern LLMs do a decent job in terms of extracting property graph models or structures from unstructured data and help transform natural language queries into Cypher, which I said earlier is the language of choice for querying a graph database like Neo4j, just like SQL is for RDBMS. For extracting a knowledge graph or a property graph from unstructured data, LLMs can work with either nodes and relationships provided by domain experts or without any information provided, only using few-shot prompting techniques with the LLM. So in this slide, take an example from the popular LLM orchestration framework LangChain. The LLM graph transformer from LangChain converts unstructured documents like PDFs, text documents, etc., to graph relationships using an LLM with a few-shot prompting strategy. This auto-extracted graph can then be stored in graph databases like Neo4j. In this example, LangChain uses an LLM graph transformer, and you could really use any modern LLM here, like GPT from OpenAI, like Claude Sonnet from Anthropic, like Llama from Meta. And then once LangChain uses this LLM graph transformer to auto-extract the graph, and the graph is created, you can store this converted graph in a graph database like Neo4j as a knowledge graph. Now, is this foolproof? Remember, with no constraints provided, the extraction of these property graphs might be non-deterministic, and nodes and relationship properties might be slightly different with each execution with this method. So what's the way around? Well, LLM graph transformer from LangChain also accepts user-defined list of nodes and relationships to constrain the knowledge graph extraction process while converting the unstructured text to a knowledge graph. So in this example, while the LLM graph transformer takes in an LLM, it also takes in these two parameters, allowed nodes, which is a Python list of existing nodes and entities defined by the business, and allowed relationships. So the LLM would, once it is extracting these nodes and entities from unstructured data, would constrain these and put this relationship as constraints within this node. So for this case, the allowed nodes are supplier, OEM, and organization, let's say, and then relationships would be has part located in and contracted on, etc. The rest of the process would still remain the same. So the property graph would be created, and then the knowledge graph would be stored in a graph database like Neo4j. So using a constrained or filtered LLM graph transformer reduces large language model hallucination. And the grounding of this knowledge is done by force using the precise ontology information supplied while the unstructured text is converted into a knowledge graph using the LLM graph transformer. Now, going to the second category of LLMs helping in graph technologies. So modern LLMs also help in generating cipher queries from natural language prompts, which could be done in spoken English as well. So taking the example of LangChain again, it uses an LLM to convert the spoken instruction to a cipher query, as well as converts the results from the graph database to natural language again. This greatly benefits business analysts who are not familiar using cipher queries and presents a reliable chat interface to extract information from a knowledge graph by business teams, business units. So modern LLMs like GPT-4 Omni, Cloud 3.5 Sonnet, Llama 3.2 from from Meta, does a fairly accurate job in translating the user query from natural spoken English to a cipher query. And it uses a chain of thought approach, which at high level consists of the following steps of converting the question first to a graph database query, executing the graph database query within the graph database like Neo4j, and then getting the result back, and then respond with natural language to the user input using query results. So this is an example of how it is done. The graph cipher QA chain, question answer chain, from LangChain provides a question answer interface for the end user, making it easy for user to ask questions in English and get answers in English. Now, remember, under the hood, the LLM converts the question to a valid cipher query. So for here, it's for Neo4j, and then getting the response back from Neo4j, and then converting it to natural language again. And the whole thing could be done simply using LangChain's graph cipher QA chain class by running chain.run, and the natural language question could be as simple as how many employees are there in total in the organization, which would result in a cipher query like this. Now let's move to the third and the final aspect where LLMs and knowledge graphs coexist and present a very, very impactful business use case. So in this case, we talk about RAG, or retrieval augmented generation. Now, RAG relies on a vector representation of unstructured data, and all natural language queries would actually query this vector database using a vector dot product or cosine similarity between vectors to present a semantic search system. So essentially what happens is LLMs are used to convert these texts into vector embeddings. These vector embeddings are then stored within a vector database. Common vector databases would be Pinecone, PGSQL with pgvector extension, Quadrant, ChromaDB, Milvus, VV8, Mongo, Elastic, etc. Now, user queries are also converted into a vector embedding, and then a similarity search is executed against the vector database. The result gets passed through an LLM, which adds context from the question and responds to the end user in a meaningful way. So that's in a nutshell what RAG is. While this works relatively well for smaller batch of unstructured text, the issue is with larger data size. With larger data size, similarity search misses the overall context. Also, context boundaries are missed by similar phrases since border constraints are not imposed. So essentially what happens is RAG gives an output where the retrieved information is used directly without inferring any border context which would have existed from the question. So how do we solve it? To solve it, Graph RAG has arrived. It's a fairly recent paper. I have given the link of the paper as well, which has arrived in 2024 actually. So it's a new approach presented in 2024, which reduces many of these issues of a naive RAG by detecting communities, which are groups of nodes or entities that are densely connected with each other, but sparsely connected with other nodes. And by identifying central nodes, which are important nodes within these communities, and then aggregate relevant information associated with these central nodes. So essentially during information retrieval phase, subgraphs are extracted from the query, and by collecting relevant facts and relationships from the subgraph query, the answer is constructed. But the magic actually happens by this community detection. So the community summaries define sections of the graph databases which are interconnected. So the answers which come in from the community are then re-ranked, and then the global answer to the question is normally presented. And of course, these are broken into two stages. One is creating these text chunks and element summaries of those chunks, which is the indexing phase. And then, of course, the query stage where the graph communities are detected within the graph database, within knowledge graph. And then LLMs use these community answers to re-rank and provide an answer which actually makes sense to the user who has asked this question. Now, this hierarchical community detection to identify clusters within the graph enriches the structure of the data and delivers a much better result compared to just a search from a summary of the full text. So community detection within these extracted chunks of text enriches the structure of data by introducing densely connected nodes at different levels of granularity. So as a whole, what happens is these knowledge graphs capture the semantic structure of the unstructured text by creating these communities. And while responses are provided back to the user, these communities provide the relevant knowledge that's needed to answer this question, rather than the full text, summary of the full text. Now, if you look at the code, it still uses a combination of an LLM graph transformer for extracting the knowledge graph and a graph cipher QA chain to present a question answer interface, but the inherent community detection is done on the graph database. So for example, in Neo4j, Louvain algorithm is one of the popular algorithms which is used to create these communities. But for the rest of the workflow, in terms of getting a natural language question answered, it uses the same LangChain's graph cipher QA chain. And when you write a chain.invoke with the query, essentially what happens is the subgraphs are created, and the knowledge graphs detects those communities and presents a global answer by selecting and ranking these answers from communities where all these knowledge nodes and relationships are tightly coupled. So this is an example of how the entire graph cipher QA chain executes. So it provides you with good details in terms of logging, and you would be able to see the kind of cipher queries which are getting returned. And then, of course, the actual knowledge which is pulled and extracted based on these communities, which are already created by this something like a Louvain algorithm within Neo4j. So to summarize, these are the three things that LLMs have come in very handy with. So extracting a knowledge graph from unstructured data, either with a constraint by using allowed nodes and allowed relationships, or without a constraint by using few-shot prompting. It comes in very handy for creating text-to-cipher queries to query a graph database. So you could actually write your query in English language, and the LLM would transform this English language into a cipher query and get the result back. And the third is graph RAG, where knowledge graphs are utilized to detect communities which are semantically relevant information and then give you a response for specific questions which are more specific and less hallucinated and more grounded in knowledge graph. So with that, I come to an end. That's all for today. Hope you liked my session and you could go back with a to-do list of what to experiment with. Here's my LinkedIn profile and my blog if you want to get in touch with me and if you want to go through my journey with these LLMs and knowledge graphs, which I've chronicled. Bye for now. Take care.